because we have two diodes, we are going to have to study for cases where either one is on or off, or both of them are on or both of them are off. We are going to have to remember that for the diode, this voltage must be higher than this voltage by what? VD on. In our case, 0.7 volts. When this happens, the diode is on. When it doesn't happen, well, the diode is off. When the diode is off, it is represented by an open circuit. When it's on, it's represented by a battery like this, with a voltage and a polarity like this. In our first case, we're going to say that what if both D1 and D2 are off? It's important to identify the voltages on the anode and the cathode of both diodes. For D1, the anode is Vin, the voltage at the cathode is Vk, for D2, the voltage at the anode is Vout, and the voltage at the cathode is VL. So I'm going to transform these circuits into the case of both of them being off. So if both diodes are off, this means that both of them must be open circuits over here. Well, if both of them are open circuits, I'm going to say for that case Vin minus Vk must be less than 0.7 volts, alright, remember here. That means that Vin minus Vk, which is equal to Vout, this is equal to Vout. Why? Because no current flows like this or like this, because this is an open circuit. That means that this point is going to have the same voltage as this point, which has the same voltage as this point, and that is Vout. So this point is Vout, therefore Vin minus 0.7, alright, must be less than Vout. I shuffle things around a bit over here. Going to work for D2 here. Now, Vout, the voltage here, minus the voltage here, Vout minus VL must be less than 0.7. That means that Vout minus, how much is VL? It's 2, alright, VB is 2, given by the exercise. So this point has the same voltage as the battery over here, the positive terminal of the battery. Less than 0.7 volts, that means that Vout must be less than 2.7. When both of these are true, it means that both of the diodes are off. That means that if I replace Vout 2.7 over here, I will have that Vin is less than 3.4 volts. That means that when this happens, Vout is going to be 0. Why Vout is going to be 0? Well, if both of them are open circuits over here, no current flows like this, or like this, or like this, or like this. No current can flow really inside the output. So if no current flows, it means that this point has to have the same voltage as this point over here, because no current flows upwards or downwards. That means that this point has a voltage of 0. Next case where this diode is off and this diode is on. In that case, this diode must be an open circuit. This diode must be a battery of the VD on voltage here, alright, this voltage. This is the polarity that's going to have. And that would mean that there would be a current flowing from the ground all the way to here, and then going all the way to here. Why? Because the diode allows the current to flow only from this point to that point. So the current has to flow like this. Well, if this is true, it must be that Vout, the voltage here, minus VL, the voltage here, must be equal to 0.7 volts. That means that Vout is going to have to be 2.7 volts, a constant value of whatever V, doesn't matter what V in here is. Well, if that were to be true, that would mean that the current had to flow from here all the way to here. That would mean that the voltage at this point had to be higher than the voltage at this point. So the voltage at the ground had to be higher than the voltage at Vout. So it would mean that 0 had to be higher than 2.7 volts plus. We know that this is impossible. That means that we cannot have this configuration over here. We can never have D1 as off and D2 as on. This can never be true in this circuit over here, because this would violate this basic principle that the diode has to allow a current to conduct from the anode to the cathode. Alright? Okay, so this configuration is impossible. Moving on to the third case. This case, D1 is on and D2 is off, so I'm going to replace both of these with a battery. Sorry, I'm going to replace only the D1 with a battery. D2 is nothing but an open circuit. That would mean that the current has to flow from the input all the way to the ground through here. It cannot go and flow through the open circuits over here. Again, I'm going to the conditions and I'm going to say that V in minus Vk, the point here, must be equal to 0.7 volts for this to be on. That would mean that Vk had to be V in minus 0.7. For V out to be off, it would mean that V out minus VL, the voltage here, should be less than 0.7 volts. That would mean that V out must be less than 2.7. Because VL is VB, 2 volts. Alright. Now, both of these conditions I suppose are true, and because the current flows from this point, or more accurately, from this point all the way to the ground, alright, from here all the way to the ground, and doesn't flow, we don't have any of it flowing through this node over here, that would mean that this is nothing but a voltage divider from circuit theory, alright? That would mean that the voltage here, V out, must be equal to Vk times R2, the voltage tied between this point and the ground, R2, over the total resistance, R1 plus R2. Alright, hope it is clear. This is basic from circuit theory. Alright, that would mean that if I go ahead and replace Vk with V in minus 0.7, I'm going to have that V out is V in minus 0.7 R2 over R1 plus R2. This would hold true when this comes from here. We're going to have to replace V out with 0.7, alright, and V out must be less to 0.7. That means that this whole thing is less than 2.7. That would mean that when V in is less than R1 plus R2 over R2 times 2.7 plus 0.7, in that case, V out would be of a constant of a varying value. It would have a linear dependence on V in of this equation, only when this would hold true. Alright, moving on to the fourth case, where both of the diodes are on. That would mean that both of the diodes must be a battery with these polarities, alright, and it should be V out, the voltage here, alright, the voltage here must be equal to VD on plus VB, alright. We measure the voltage at the output over here in respect to the ground, alright. This is counted in respect to the ground, so it is like we measure in parallel to two batteries. So that would mean that V out must be equal to VD on plus VB. How much is VD on? 0.7 plus VB, which is 2.7 volts. So previously, when this was off, this was on and the voltage here at the input was rising and rising and rising, and the voltage here at the output was following the input linearly. If you remember from here, alright, the V out is following, alright, let me erase most of this crap over here. If we remember from previously, the voltage at the output was following linearly the voltage at the input. It was following it up until this point, where V in was equal to this thing over here. That will mean, in our case over here, up until V out turns out to be 2.7 volts. When will this happen? This will happen when V in is going to be more or equal than R1 plus R2 over R2 times 2.7 plus 0.7 volts. Alright, more or equal now. Before it was less. That would mean that when V out is rising and rising and rising up until this condition holds true, Vout is going to have a constant value of 2.7, and from there onwards, it would be that Vin is going to be this thing over here. Now, a good question is, well, I noticed that Vout has a constant value, and Vin is increasing constantly from this point onwards. It can increase. How is this possible? Well, this is possible because the voltage here at the point K is going to change its value in order to uphold true this thing. The V in minus Vk is equal to 0.7. This must also always be true. However much V in is increasing, Vk will also increase to uphold this condition over here. As long as Vk increases, that would change the current that flows like this. However, the voltage here would always have to be 2.7. If the voltage here is always 2.7, this Vk increases with increasing Vin, that would mean that the current here is going to change, alright, this current is going to vary, and this will change the current that flows from this node over here, because this point would have a constant current, alright, the current would be constant. Why? Because Vout would have a constant value. So this is a cool little, maybe you will be asked in a quiz or something like that, so it's cool to remember this. Alright. Now to sum up what we did, we know with all of our cases, we have that Vout will be 0 for Vin less than 3.4. Both of the diodes will be off. If D2 is on and D1 is off, this is an impossible configuration, it cannot happen. So ignore this. When Vin reaches 3.4 and goes upwards, alright, up until some point here, Vout is going to follow linearly Vin, alright, with this equation. And when Vin is more or equal than this value over here, when it reaches this thing, this value over here, then Vout is going to have a constant value of 2.7, this is volts. So we're going to have a Vout, and let's show it like this, a Vout and a Vin diagram. When Vin is less than how much? 3.4. 3.4. Vout is going to be 0. When it goes further than 3.4 up until this point here, I'll name this 1. Alright, I'm not going to write it again, all of it. Up until when it reaches this thing, I'll name this 1. This is going to have a linear dependence. It's going to rise up until a point here. How much is this point? This point is 2.7 volts. So this is 2. Alright, this is some terrible mouse writing. 2.7 volts. When it reaches 2.7 volts, and then it will have a constant value, however much Vin increases, alright? From this point onwards, Vout is going to have a constant value of 2.7 volts. And that was it. That's basically how to solve diode circuits that are a bit more complex, that have 2 diodes or more, alright? If you had more diodes, we would have to study more cases. Alright, check out the diode playlist over here for more diode videos. Study well and take care. Bye bye.